Alrighty, what is going on, everyone? So today we have another buck converter design that we're going to be taking a look at. So right now we're looking here at the finished PCB. So what I'm going to be doing is taking you through the entire design process. So we're going to go over the circuit design for this. We're going to be going over like the data sheet for the chip we're using. I have a whole bunch of component calculations that I'm going to be walking through. And so basically, we're going to take you all the way from idea to manufacture on this board. Before we go any further though, please go ahead and drop a like on the video. That helps my channel out a ton. And subscribe if you'd like to stay up to date with any future videos. I like to drop a whole bunch of project videos showing you how to design stuff on this channel. So with that stuff out of the way, let's just jump right into it. So I think the first place we'll start here is I have like a little brief summary of some of the details for the project that I have listed here. So what we're going to be doing is taking 24 volts on the input, and then we're going to be bucking that down to 5 volts on the output. So the first thing I'll talk about here is that I put this little squiggly mark for it's roughly 24 volts. So if we're imagine hooking a 24 volt brick power supply up to this board. So typically out of a brick you should expect anywhere from 22 to 26 volts. So that's kind of the bounds that I have set up for this like power supply. So typically whenever you're designing, it'll ask you for what's the VN min and what's the VN max. And so that's why I have this range right here. The other thing I put on the output is 5 volts plus or minus 3%. So that gives us, that's just the margin of error. So that means what we're outputting anywhere from like 4.9 volts, anywhere to like 5.1, something like that. So that's kind of what we're talking about with the margin here. Then we have an I out max of 300 milliamps. So that's the maximum amount of current that this power supply can provide. Then we have an output voltage ripple of 1%. And then finally, we have a switching frequency of 1000 kilohertz or 1 megahertz. Those are pretty much all the major project details. Stuff I'll add in here real quickly. So we're gonna have some mounting holes on this board, which is something I'll be featuring a lot on this future projects, because pretty much all PCBs have mounting holes. And then that's pretty much it. Then I want to make sure we have an input and output connector just for the sake of having something, I think. But other than that, that's pretty much all the stuff I guess we need to know before we can start designing our power supply. Okay, so now I just want to dive into our circuit, and I want to give like a detailed breakdown of kind of what we're seeing here. And so I have some notes that I kind of want to go over and kind of explain what we're looking at here. So the first thing we're going to talk about is the controller IC, which is U101, which is this puppy right here. Let's see, so U101 is our switcher IC, buck converter IC, or all the different names that you might hear this by. Basically, it has its main job is just to control the current through our output inductor, right? Which is L1 right here. So basically this chip will monitor the input and the output, and then it controls the current through the output inductor right there. So this particular chip though has two internal MOSFETs that allow to control the current through the inductor L1. So if you remember, if you watched the previous buck converter design guide that I made, the whole project tutorial, you'll notice that there was a rectifier diode on the output on the old one. See, this one doesn't have that because this one is known as this one uses what is known as synchronous rectification. So it utilizes two MOSFETs. And if you recall, I made a buck converter basics video back a while ago, and I talked about how there's more than one type of buck converter. There's one that has asynchronous rectification and one that has synchronous rectification. Asynchronous just means it uses a diode. Synchronous means it uses another MOSFET, so the switch opens and closes. Let me see if I can go and find right here, right? So typically, or not typically, but commonly, you'll see a buck converter circuit that looks like this, where you have a rectifier diode that allows, so when the switch is open, that closes the circuit and allows current to flow, just like in this red box right here, right? With synchronous rectification, you have another MOSFET here. So if this one's open, this one closes. And what you're supposed to do is get increased performance out of this. Maybe you can have a smaller package size because your MOSFETs might be just a tad bit smaller than the diode if your currents are really, really high. So there's a couple of different reasons why you might want to do that. So hopping back over here to our circuit design notes, that's what this little note here, this one has 2 internal MOSFETs. And I guess another one I'll make is, this is what is known as a converter chip. So you have 3 major families in the buck, you call it a buck regulator. So you have buck regulators, and within that family you have converter, controller, module. And this one is known as a converter, which means it just has the MOSFETs are internal to it. So that's why we don't see them in the circuit, because there's 2 MOSFETs inside this puppy. And so we don't actually have to pick our MOSFETs. We don't have to do anything like that. So that's kind of what that means. So that's what this note means. It has 2 internal MOSFETs that allow it to control the current through the inductor L1. And we'll take a look at the inside of this chip later on when I go into the LMR 36503. I think I should even have, I'll even look at the, yeah, we'll go inside. There's a part of the data sheet we'll check out. So yeah, that's the first note here, is that there's 2 internal MOSFETs that control the current through the inductor O1. It monitors the input voltage and the output voltage and adjusts the duty cycle accordingly. So like I said, yeah, this thing's only job is to control the current through the inductor and ensure that we get 5 volts on our output. Alrighty, so moving on, let's just take a look at the input side. So we have a two position connector, vertical header from Molex. And that's P1 right here. And in this particular case, I just picked something that had the appropriate voltage and current ratings. So if we click on this, you'll just look at 600 volts, 8.5 amps, and so I knew that it was going to be able to handle our input current. It's a 2-position connector, because all we do is power. We have one obviously connected to our input voltage, and the other is connected to ground. Okay. And then there's the part number right there if you're curious. So input side, now the next thing we have is the smoothing and or bypass capacitor. We have a smoothing capacitor and a bypass capacitor, I should say. So we have C2 and C3. This helps eliminate noise and gives the IC a clean signal to work with. This also does a job of supplying input current whenever one of the switches is open and closed. So we're talking about C2 and C3 right here. So this one's going to be our input capacitor. This is going to be the bypass capacitor. So the notes I have here, the bypass capacitor's job is to eliminate noise. So that's what this smaller one is here, is like high frequency, high transients can affect how this controller works. And so like it's like basically input noise into the chip. And so that's why we put this bypass capacitor to try to short that stuff to ground. And this one's job is to supply any of the current, or supply the just help smooth out the voltage waveform, right, of our 24 volt signal. And then moving on, we have a voltage divider, R1, R2, sends the chip into under voltage lockout if input voltage falls below a certain level. So yeah, that's kind of what this thing's going here. So, and we'll take a look at this chip when we take a look under the hood. But basically, whenever the voltage at this pin drops below a certain level, the chip overall shuts down. And so what we're doing is we're taking a fraction of 24 volts. And if this pin drops below 1.4 volts, then it shuts down. That's kind of what we're doing right here. And I'll explain how I did the calculations for that as well. Lastly, we have the timing capacitor, C7. So that's the switching frequency of the chip. So if you see here, we have pin 7 shorted to pin 1, and then we have a capacitor right here. So this is what sets the switching frequency of the chip. All right, so moving on to the output side. So on the output side, inductor L1 should be familiar. This looks exactly like, everyone knows what this looks like in the buck converter. Basically, the other buck converter components are inside the chip U101, and so when we take a look at those, it'll make perfect sense. The voltage divider on the output side sends a feedback signal to the chip U101 to help it regulate the output voltage. So it's much like going to this. So this is the voltage divider on the output side. So it's much like what we have going on the input side, is that we have We're just trying to monitor the output voltage, and it's sending a signal back into our chip and then basically allowing it to adjust the duty cycle accordingly in order to maintain that constant 5 volts on the output for us. For the voltage rider, we have an array of smoothing capacitors, C4, C5, C6, to filter the output and give a clean signal. So they're doing a similar job as the input capacitor. So this one bigger capacitor right here is helping smooth out that 5 volt signal, and then we have these other two here which are just trying to filter out these high frequency noise signals and make sure we have a very clean, smooth 5 volt signal going into the output. So we just have an array of filtering caps right there. Then we have the bootstrap capacitor, which is C1, which applies the voltage needed to drive the MOSFETs. And then we'll take a look at what's going on there specifically under the hood. So this was a pretty interesting, this is a feature you'll see in a whole bunch of buck converters, especially newer buck converters. Really what it is a power good. They call it a flag, right? So it just sends like a logic high or a logic low signal, and basically all it does is tell you that the buck converter is running or it's not running. So typically this would be connected to the GPIO pin of a processor, so it basically allows our processor to monitor whether or not one of its power supplies are working on the board. Say this power supply is powering some peripheral and the power supply like shuts off for some reason, then you can understand like what's going on here, because it'll send a signal back to the processor, right? Like I said, this allows us to monitor the power supply and see if it's operational. So that's what this signal is right here, this P good here. So typically this is what will be going back into a processor. We don't have a processor on this board. It pretty much covers all the components we're using. And then if you see here, I have 4 mounting holes that are placed on the schematic, and then so they'll show up in the layout. Of course, we have the same connector on the output as we do on the input because it works fine. So yeah, those are the main details of this circuit that I wanted to cover. I said, if you have questions about this stuff, go ahead and drop a comment down below, and I'm extremely responsive with all the type stuff. And also, if you have any other projects you want to see on this channel, drop a comment down below and I'll definitely feature them on there. So alrighty, so next up we're going to be taking a look at the inside of our LMR 36503 chip. That way I think it'll help give us a better understanding of kind of how the circuit works as a whole when you kind of look under the hood. So here we have, I'll actually go to the top of this real quick for you. So this is the data sheet for our LMR 36503. So I'm just going to be kind of highlighting some brief summary points for kind of how this thing works. And then that way you understand kind of how it fits into the broader context of the circuit for us. So the first set of notes here, something I pulled from that first page, was just the summary and background, which kind of gives us some basic operating details of the chip. So as I mentioned before, this chip is known as a synchronous converter. So not only does it have 2 MOSFETs, but the MOSFETs are integrated inside the chip. So that means we don't actually have to pick any MOSFETs for our circuit. They're already chosen for us. So this is an advantage in that our design is much simpler, but it's a disadvantage in that we have less flexibility with our design. And so it's kind of a trade-off there. And kind of as I mentioned before, so basically a good way to understand what this chip actually is a very simple computer that monitors the input and output voltages and controls the switching of the MOSFETs. Brief description of the chip. So this is kind of stuff I looked at whenever I was coming up with the actual project. So these are things you would look at if you're trying to determine whether this chip would fit on your design parameters, right? Of what you need out of your power supply. So here it gives us an input voltage range. So it's 3 volts all the way up to 65 volts. So that means if your input for some reason is greater than 65 volts, don't pick this chip because it won't be able to handle it. And then we have a 300 milliamp max output current. So this is usually dictated by a few internal components. Maybe they have like a diode or something on the inside of the chip that feeds some type of logic. It's going to have to do with our 2 integrated MOSFETs that have been chosen for us. Might only have current limits of around 300 milliamps or something like that. So that's kind of why we have a max output current limit right there. Those are usually the components that are determined by that. Usually it's semiconductor related components. As I mentioned a couple times before, we are using synchronous rectification. And then this one has what is known as an adjustable switching frequency. It goes 200 kilohertz all the way up to 2.2 megahertz. And so this is a feature you'll see on a lot of chips as well, because there's a relationship between switching frequency, converter efficiency, and like overall what they call like solution size, which is like how big your output inductor is, how big your capacitors and stuff are on the output. And so this is a feature you'll see on a lot of newer stuff. So it just gives you more flexibility with your design choice. And I believe we went with 1,000 kilohertz or 1 megahertz, so it's just right in the middle of that range. I would say if my switching frequency is below 200 kilohertz or above or even I say below, or close to 200 kilohertz or somewhere pushing it like 2.1 megahertz, I might find another chip that can go a little bit higher. That way we can kind of account for any sort of deviations in the manufacturing of the chip. Maybe something only gets up to like 2.19 megahertz or something like that, and you don't want to be operating at 2.2. You don't want your design to be designed for 2.2 when you can only operate at like 2.19, if that makes sense. So typical engineering stuff. Let's quickly go over the pin functions here, right? So let me see. So we have all these pins: the VN, the enable under voltage lockout pin, the timing resistor, we have VCC, ground feedback, P good, switch, and boot pins. Right, I don't think it gives us a nice convenient package that we can take a look at, but don't worry, we have everything noted down here. So VN is the power input pin, so that's where you see here where I have our 24 volts being input in, so that's pin 4 right here. Then we have the enable, which is the chip enable pin. Pull, says the notes say pull below 0.4 volts to disable the chip. So this is what I was talking about earlier. And the reason we have this voltage divider is whatever, and we'll see this in the component calculations notes later on, but whatever we have this voltage divider set at, whenever 24 volts drops down, let's say it's like 12 volts or something, then this will eventually fall below 0.4 volts and it will cause the chip to go into under voltage lockout. All right, next is going to be the timing resistor input. Sets the switching frequency of the chip. So notice there's supposed to be a timing resistor here, but I don't have one in my circuit, and we'll see why I didn't put one in later on when we review the component calculations section of the project. And I'll explain why we don't need one, but we do need a capacitor right here. Let's see. Next we have VCC internal LDO output. So honestly don't worry about what any of that stuff means. That's beyond the scope of this project. It's just internal stuff that we got to make sure we know what to do with, and luckily the datasheet tells us exactly what to do with that pin. So SW, the SW pin or the switch node pin, is basically our converter output. So this is what I have connected to the output inductor. So basically we have VN coming in, and then we have it exiting to our output inductor, and then there's some internal MOSFETs that we'll take a look at in a second. We'll see exactly how the circuit is constructed. So next up we have our bootstrap capacitor input, which is right here. So if you remember in the notes, the bootstrap capacitor is what actually supplies the voltage that is necessary to drive the MOSFETs. And we'll see kind of how that works on the inside as well. And then P good, we have the power good flag output, and I explained how that worked in the circuit design notes section, which is a little bit earlier. So right, it just sends us a logical high or low signal depending on whether the power supply is actually functioning or not. And then lastly, we have our FB pin, or the output voltage feedback, which monitors the output voltage. And so that's this one right here. So that's where we have the output right here being voltage divided down and then fed back into our chip so that it can monitor the output voltage. Alrighty, so next up, let's take a look at the functional block diagram. So this is actually an exciting part because they actually show you what the chip looks like on the inside, at least a functional block diagram of it, right? So the first things I want to point out, right? So let's just take a quick inventory of all our locations of all the pins that we just took a look at. So you have VN right here, then you have switch right here, then you have ground right here, you have our P good right here. It looks like another ground right here. I think those are combined because I only remember one ground pin in that circuit. Then we have our enable, which just sends a signal into our enable. Then we have our RT pin, which is tied to an oscillator, which is what goes into a whole bunch of op amps and air amplifiers and control logic and stuff. And that's what drives our That's what controls our switching frequency, right? So just a quick, I want to try to kind of bridge the gap here between what's going on the inside and the outside chip. So let's start here at the VN pin. So we have VN, and let's go back to our circuit. So you have VN coming in right here. And then we see, here's our first MOSFET, here's our second MOSFET, right? And so let's also try to look at, let's go to our buck converter basics. So, okay, right here, right? So here's MOSFET 1, MOSFET 2. And so you see how the output inductor is sandwiched between these two MOSFETs. So it's the same thing that's going on here. Switch node is sandwiched between these two MOSFETs. They're just oriented a little bit differently. And then so you have the switch node, which again recall switch node right here. We have the inductor, right? So it's the same exact circuit setup as what we just looked at. It's just oriented just a tad bit differently, right? So we have the input voltage coming in, first MOSFET to go to this is when the inductor is charging. And then this one opens, and then you have this one closes, which shorts the inductor to ground. And that's kind of how the whole circuit works, right? So hopefully this kind of bridged the gap to, like, because a lot of times you'll look at the circuit and be like, this looks nothing like any buck converter I've ever seen. And it's just because a lot of the stuff is kind of hidden behind this little yellow square, which is the representation for the chip. Okay, so I hope that kind of helped make sense as to what's going on here. And maybe you have the full picture of like, okay, now I finally see the full synchronous buck converter circuit now that we've seen what's going on under the chip. So hopefully that helped you out a lot there. So just go and take a look at the notes I have here. So the feedback signal is fed into an air amplifier, whereas compared to a 1-volt signal, the EA output is then sent to the CLD. So that's actually another cool section I want to take a look at as well. So what I say, the feedback signal, right? So this is the signal, this signal right here is fed into an air amplifier. So that's this thing right here, right? So the feedback signal, right? This is a fraction of our output voltage is fed into an air amplifier, and it's compared to what I say is a constant 1-volt signal. I don't know where this 1-volt signal comes from, but it's every buck converter has something exactly like this, where there's some type of constant 1-volt, 0.34 volt, 0.325 volt signal always present on this comparison node, right? So you have this being compared to some constant signal, and then basically kind of what you do is this information is either the signal, basically the output is either high or low, and it's fed into a bunch of other complicated parts of a circuit through another air amplifier, and then this is sent ultimately to the CLD, which is the control logic and driver, right? And so this is where a bunch of computery computations are going on, and then those ultimately tell the MOSFETs to be either the gate signals to be either driven high or low, which one's supposed to be high and low. And then up here, if you look, the bootstrap pin, remember the bootstrap pin is where we have this capacitor connected. Remember I said the bootstrap capacitor is what supplies the voltage to the MOSFETs, right? So if you think about this CLD trying to supply a whole bunch of voltage and current, right? Because if you know a lot of stuff about MOSFETs, you understand that there's like an initial surge current going on. So there's actually some very high transient currents present in these gate drive signals right here, and putting that stress on just being able to it's much easier to use a capacitor to supply that than it is to actually have internal stuff going on, right? So that's kind of where that comes from. So that's kind of, if you kind of see all the pieces are kind of finally like coming together, and you're kind of getting a good working understanding of kind of how this whole chip kind of functions, what all the little pieces are doing, except for VCC. Don't ask me what VCC does. I'm kind of kidding. If you look, VCC has something to do with our timing chip. I think it goes in somewhere. It ends up going V out bias, right? So that's where those signals kind of combine with somewhere over there. And there's a bunch of other nifty like little parts, like you have soft start and current limit and stuff, current limitation stuff that's going on here, which you don't really need to worry too much about this yet. Maybe in later projects we'll talk more about this stuff, but hopefully things are becoming more and more clear as to what this chip's doing and all the cool stuff that's going on. Track capacitor connects to the CLD, see how it supplies the gate drive voltage for the MOSFET. That's cool, we just talked about that. Note the different little functional groups. They said P good, timing circuit, LDO. We'll go over any of that. So P good, again, this looks like more like a logic type block, and then it's just sending an output signal to either low or high, and you have a little MOSFET right here that's sending that signal. It has to do with our feedback and V out bias. Again, I don't exactly know what's going on here, but just understand, like, it's like a cool little like functional group in the corner that is kind of doing its own little thing here. That's kind of how these chips are designed right here. Then you have an LDO, which supplies some other stuff to, I don't really know, like this is just like another signal, right? That's used throughout like the rest of the circuit. I think this might be how they generate their 1-volt signal for us. So then try to make out the synchronous buck converter circuit. So that's what we spent a little bit of time right in the beginning of trying to explain and bridge that gap. So yeah, I think this is a really good place. I think this is all that you kind of need in order to understand, have a good understanding, I should say, of what's going on inside the chip and how it applies to the rest of our circuit. So you can kind of see with how this yellow square interacts with all the other components on our circuit for us, right? So hopefully maybe that gives you a better context for how everything fits into place here. And then when we start doing component calculations, I think you'll understand like, oh, okay, this is why this is this values, or have a pretty good understanding of like, oh, okay, so this thing kind of, this component that we're calculating for, it goes here and stuff, and here's kind of what it does. So hopefully that cleared things up for you a whole bunch. And yeah, so the next thing we're gonna be doing is working on those component calculations. Okie dokie, so the next step in this project is going to be to do the component selection. So basically what we're going to do is I'm going to go through each and every one of these components we see in our schematic, and I'm going to show you how you go about selecting them. So the datasheet actually provides a really good guide. They give you a lot of the important formulas and equations that you need. Then there's also some extra details that I'll be adding in that I have acquired from my experience as an electrical engineer that will help us pencil in some of the other parameters for our components. So I have a whole list of notes here, and let's just jump right into it. So on the data sheet, the first thing they will tell you to select is going to be a switching frequency. So let's zoom in on this a little bit first. So yeah, so the notes I have here, the choice between, or a switching frequency basically helps you choose between, like it's basically a trade-off between solution size and efficiency. So a lower switching frequency means larger inductor and output capacitor, and a higher switching frequency means increased switching losses. And that's what this F sub SW means, is the switching frequency, if you're wondering there. So for this project, I chose a value of 1,000 kilohertz or 1 megahertz. And that's just more of a like middle of the road value that you'll see for buck converters. So we won't get too big of an inductor or output capacitor, and our efficiency won't be too bad, right? So it's kind of like a jack of all trades, master of none kind of approach to this design. And typically what you might do is, if this were, if you'd have more of a context for this power supply that might help you choose whether you want something more efficient or more size effective, you would say, right? But for now, we're just kind of picking those sort of arbitrarily, but we'll see how they affect other design choices. So whenever it comes to setting the switching frequency, the data sheet will refer you to table 8-1. There's also an equation in the data sheet, if I remember correctly, but I don't know what it is. And the reason I don't know what it is because if you look on the table, it tells you that if you want to set the switching frequency to 1 megahertz, which is what we want to set it to, then you just connect the RT input to the VCC pin, right? So going on our schematic, you see that I've shorted VCC to the RT pin, and that's what sets our switching frequency at 1 megahertz, okay? So you don't actually need a resistor or anything like that, right? And you see, if you want it to be 2.2 megahertz, you just pull the RT input to ground. So yeah, that's kind of all we have to do, honestly. So it's actually pretty simple. This capacitor will be chosen later on whenever we get to it, so don't worry about that. We'll come back to it. So next up, we are going to be setting the output voltage. So the output voltage is set through an external resistor divider, our feedback top and our feedback bottom. So on our schematic, this is our feedback top and this is our feedback bottom. And the recommended value for our feedback top is 100K to 1 mega ohm. So I just picked 100 kilo ohms, and this will be a trade-off between, this is a choice between noise sensitivity and efficiency again, right? So a lower resistor value means you'll have a higher amount of current flowing through the R feedback top. So it'll also be more sensitive to change, but it'll be less efficient, right? So more power is being dissipated through this resistor. Again, it's sort of a choice that if we had a greater context for our power supply, we can kind of choose between those two. But for now, I think what do we end up doing? Like we did 100K, right? Yeah, just a very simple 100K. So we choose for our feedback top to be 100 kilo ohms. And then the equation that the datasheet gives us is that R feedback bottom is equal to R feedback top divided by V out over V ref minus 1. And in this case, we have V out is equal to 5 volts, which is what we set at the beginning of the project. We said we want to make a 5 volt power supply. So there you go. V ref is equal to 1 volt. This value is found in the data sheet. So that's where we got that from. And then our feedback top is 100 kilo ohms. And we just arbitrarily set that value. So when you plug these in, do the math, you get 25 kilo ohms for your package size. And I ended up going with 24.9K because that was the closest nominal value I could find. So typically what happens whenever you're doing the math here is you'll get some really specific number. The supplier, someone like DigiKey, you go scrolling through their website and you might not see they have the exact value you need. So you just find the closest value, and that usually works out okay. So 25K works just fine. Typically my suggestion with all surface mount components that are packaged like this, resistors and capacitors specifically, I guess I should say, is that you want to go start out with an 0603 package, because this is a package size that it's not too big where you're gonna have problems placing the component, and it's not too small where there's this neat routing trick you can do where you can route in between pads. And 0603 is about as small as you can get before you're unable to route through the pads, and sometimes route in between the pads, I mean, whenever you're doing your PCB layout portion. So start out with 0603, and then you can shrink it down if necessary. So that's what I'll say about that. Go with a 1% tolerance on this one. It's a pretty standard tolerance. It won't make sure our resistor isn't crazy expensive. Again, this value would only matter more depending on what our output tolerance is. So yeah, 1% tolerance is more than fine here. And then make sure the power rating for both resistors is appropriate. And of course, all these recommendations are for both resistors. Make sure both are 0603, 1% tolerance. For your power rating, I think 1/10 of a watt is more than enough, because we're only have a 5 volt voltage drop across both of these combined. It's like 124.9 kilo ohms of resistance. And so it's not like you're generating that much power here. So I think we're more than fine there. So that's pretty much all the stuff you need to know for setting the output voltage. All right, so moving on, we have the output inductor selection. So the main two parameters for consideration are inductance and saturation current. I would also say that current rating is also an important factor, but we'll kind of get into what these values actually means. So inductance is kind of self-explanatory. It's sort of like the value of the inductor, sort of like what is the resistance? What does that mean? Just think of it as the value for the resistance. But saturation current, what that is basically what happens is if your current gets too high, your inductor stops becoming an inductor at some current level. And so what the saturation current does, so basically what really happens is your inductance will start to drop as your current goes up or past a certain point. And so what saturation current is it tells you at what point your inductor is no longer an inductor. So what you want to do is make sure that the saturation current level is higher than the peak current level you'll ever experience. And we'll kind of get into how you calculate that. A little short explanation is that you have your maximum output current plus 1/2 ripple current, right? So say your output current is 300 milliamps and your ripple current is 100 milliamps. Your peak current that you're ever going to experience is 350 milliamps. All right. So that's kind of so your saturation current level should be like 350 milliamps or something like that. That's kind of how you go about choosing that. And then make sure your current rating in general is just your average output current. So our average output current is 300 milliamps. So what we would do is pick something with a current rating of around 300 milliamps with a saturation current rating greater than 350 milliamp. And we'll probably revisit those two things in a bit, but that was just a quick explanation. So inductance is based on the desired peak-to-peak ripple current. So usually 20 to 40%. This is what I would call is like an industry standard. This is what most power supplies are capable of achieving. And this is what is satisfactory for other parts, like, for example, whatever else you're supplying power to can usually handle a ripple current of about 30%. Well, I should say 30% on the inductor, because we have an output capacitor that's supposed to smooth this 30% out to, a whopping like 1% or something, right? So it's typically what most output capacitors can handle, I should have said. 30% is a fine value. So then they give you this formula right here, which is Vin minus Vout over switching frequency times K, which is going to be our ripple percentage, times Iout max, times Vout over Vin. So when you plug those numbers in, so in this particular project, we specified that 24 volts is going to be our input voltage, 5 volts is our output voltage. Here's our switching frequency, which is 1000 kilohertz. We have a K value of 0.3, which is 30%, and we have an Iout max of 0.3 amps or 300 milliamps. And then we have Vout, which is 20. Oh, see, this is incorrect. This should be 5 volts over 24 volts. So don't worry, I believe I did this math correctly. I just noticed I made an error in that. So don't worry, this will, because I do remember actually making this mistake. I just never corrected it. So don't worry, 43.98 microhenries is what we got. And then again, this what you typically do is, like I said, we get this really specific value. So you go to your supplier website and you find out, you just pick the closest nominal value. So I don't know what did we end up picking in this case? 47 microhenries. Okay, so there you go. That's what we end up doing. Saturation current rating should be greater than the output current, 300 milliamps. In this case, I would say go up to like 350 or whatever. I don't know if I even have my saturation current listed on here. It doesn't tell me what I put for my saturation current, but that's what you should pick, is something that's over your peak current that your inductor will ever experience, and make sure your current rating is greater than your Iout max. Output capacitor selection, right? So I should probably be going through this, and I mean, some of these are pretty obvious, right? Like we know what our divider is and we know what that stuff is. So the output capacitor is going to be this capacitor right here, and I just slapped on these other ones right here with a 0.1 and 0.01 microfarad, and that's for noise and other transients, right? So this C4 is what we're solving for now. So output capacitor selection, reference table 9.2 for output capacitor selection. Also an additional 1 nanofarad to 100 nanofarad capacitor can help with transients. So this is actually pretty nice when they give you a table. We use table 9-1 as well as our previous 5 volt 1 amp power supply design as a reference. And this is a good note actually, because one thing you might notice is some data sheets not all data sheets are created equally, I can say. Some of them have way better instructions and a bunch of little caveat notes and explanations on them than others. Just because as time, passes on, you have new engineers writing these notes, you have new things are learned, companies get feedback, and so they try to improve their data sheets constantly, right? So that's why it's good to design a whole bunch of different power supplies, look at a whole bunch of different data sheets, because then you can always reference them and kind of piece together a more holistic understanding of like, for example, power supply design, right? By this note here is we know that we've designed 5 volt 1 amp power supplies as a reference. And so this one's 5 volt 300 milliamps, which isn't too much different than what we're already working with, like the ripple voltage is about the same. The only thing that's different is our ripple current. And so again, like at the end of the day, use it as a reference, use your previous design experience and apply it to future designs. So according to table 9-1, looks like we chose a 22 microfarad capacitor was chosen. And then I have some notes here where I said, make sure your ripple current is able to handle the amount of output current that we're talking about. And so ripple current is also related to our inductor size. And so 20% ripple current, desired peak to peak ripple current. So 30% of 300 milliamps is we'll call it 33%, and that's roughly 100 milliamps. So that's the amount of ripple current that our output capacitor should be experiencing. So make sure ripple current rated appropriately. Package size, this is kind of what I talked about with the resistors. I would say, well, this is going to be, let me check this. So this one is a ceramic capacitor, right? So this is, and I believe this is a surface mount. component. So yeah, the package is, this one's ended up being a 1206. But I would say, again, start with an 0603. And I think, honestly, I was just lazy and used a leftover 1206 instead of making a new one. But start with an 0603 because they're, like I said, they're really easy to place. And they have more routing flexibility than anything that's smaller. So it's kind of the best of both worlds. Start with an 0603. If you have to go smaller, do it. I wouldn't see a reason why you necessarily need to go bigger. Maybe you do if you have routing troubles, but this board is extremely simple. So I think you should be fine with an 0603. And then lastly, your voltage rating. So the output voltage that our capacitors are experiencing is about 5 volts, right? Plus or minus some ripple, plus or minus some transients. So just make sure it's nice. And above that, I mean, what did I choose? My voltage rating is 10 volts. So there you go. But it's super easy to find something that's 50 volts at the same exact package size. Alrighty, now on to the input capacitor. So real quick, let's go back to our circuit. So input capacitor is going to be C2 right here. So that's what we're working on now. So a minimum of 2.2 microfarad capacitor should be used on the input side. So let's go just take a look at this. It looks like I ended up using 4.7. Again, I think I just used a leftover capacitor that I already made in my library. I mean, that's kind of the point of making parts, is that you get to reuse them. Hopefully you don't have to make new parts every time. Looks like the data sheet recommends something that's made out of X7R material. So this is a type of ceramic capacitor. You can easily filter this on supplier websites. Voltage rating needs to be greater than VN max, and so I think that was like 26 volts, and so I want to say this one is rated at, let's check it out, 50 volts. So yeah, like I said, it's super easy to find something that's rated appropriately. And I say package, I recommend an 0603. Again, I think I was lazy and went with the 1206 that was left over, but don't worry, I'm working on new library parts and I will be reflecting my design recommendations in my projects instead of being lazy. Moving on, it says an additional 100 nanofarad capacitor should be used to bypass higher frequencies. So yeah, this is another common thing you'll see in designs is they call, so this is your input capacitor, and this is referred to as a bypass capacitor. And here I have this little note that says place as close to the regulator as possible. And I would do that for both of these capacitors actually. Put them as close to this as possible, and that's in the layout. So we'll get to the layout and talk about it. On the schematic, it doesn't actually matter because, you know, this doesn't, you can put these anywhere you want as long as the connection's right. Oh yeah, real quick while we're on this. So yeah, the other two, the 100 nanofarad capacitor that it was recommended for the output, that's what those two are right there. So that's, I placed them as well. So that's kind of what we're looking at here. So this is the bypass one, make it ceramic. Make sure the voltage rating is appropriate. 0603 package is what you should probably start with. And then, yeah, this note, usually this came from the data sheet. So they'll give you recommendations for that as well. Pretty much everything you know for the input capacitance side of things. All right, so now we are on to the bootstrap capacitor. So looking at what the bootstrap capacitor is, that's good old C1 right here, the 0.1 microfarad cap that is tied between the bootstrap pin and our switch node right here. So bootstrap capacitor. So looks like the notes are the LMR 36503 needs a bootstrap capacitor connected between the boot and switch pins. The bootstrap capacitor supplies the voltage needed to drive the MOSFET. So if you recall from the section where we just talked about the inner workings of the LMR 36503, we kind of saw where the bootstrap capacitor pin tied into our like CLD, central logic device, or CLB or whatever, central logic device. And so basically what the logic device used all the voltage that the capacitor was storing, all the charge it was storing, and that's what it uses to drive the MOSFETs. And so what you use, you charge up that capacitor to whatever voltage you need, and then that's what drives the MOSFET. So I guess that's just the way they decided to make it. Don't really know enough about the inside of the chips why they do that, but that's very common in pretty much all common power supply designs. So it says choose a 100 nanofarad capacitor for this application, and I think I went with 0.1 microfarads. So I think that's 100 nanofarads. Important things, notes it makes for this is make sure it's at least 16 volts. And maybe one thing I don't know if we covered in here is, so maybe we can go back to the inside of this chip. So looking at the inside of this chip, so you have two MOSFETs here, And we haven't really talked a lot about MOSFETs on this channel. At least we haven't had to work with them directly. We had to work with them a little bit, but if you recall way back to maybe some of my flyback converter designs, typically MOSFET, the gate drive voltage that is necessary to drive it to where it conducts, and I would use the term conducts significantly, to where its RDS on is extremely low, that's usually about 10 volts. Right, so what that means is your capacitor right here will be charged to more or less, 10, maybe 12 volts. It depends on what the MOSFET rating is. It could be all the way up to 16, honestly, because that's what they're suggesting you make sure your capacitor is rated as, right? So what I'm saying is, so this capacitor is probably charged up to almost up to 16 volts, right? And that's what is being, 16 volts is what is being used to drive our MOSFETs that are on the inside of our chip. So you're using 16 volts to charge these MOSFETs right here, and that's coming from the bootstrap capacitor. So that's why we need to have it rated at least 16 volts. Let's check the one that I did on mine. I think mine's probably like 50. So yeah, so it's like, again, super easy to find something like that. Again, I said go with 06, 03 package. Start out with that because of the ease of place, because it's easy to place, and the routing flexibility that it gives you. And then they say make sure it is an X7R material, or I think that's just the note I put just because they've suggested that and the other parts of the data sheet. So it seems like a trustworthy material, you know? All right, and moving on, the VCC capacitor. Okay, so VCC capacitor, that is C7 right here, the one that is 1 microfarad. And if you go ahead and read the data sheet, it says the LMR 36503 has an internal LDO that the VCC pin connects to. The other internal connects to the other internal control circuits. A 1 microfarad capacitor was chosen for this application. So they just straight up tell us, make sure you have a 1 microfarad capacitor tied to the VCC pin. And so that's what we did. They made it easy for us. They suggest that it's rated also at least 16 volts. And I say, again, go with a 0603 package and an X7R material. I think mine's probably rated higher than 16 volts, just because it's easy to find that. And yeah, that's pretty much everything you need to know for the VCC capacitor. Again, it's pretty simple, pretty straightforward. And lastly, we're going to take a look at the external UVLO, or under voltage lockout is what that stands for. So that's what this resistor divider here is. It sets the level at which our power supply shuts down, meaning say this value drops below 24 volts and it's like, say it's like 16 volts, instead of like stressing out our chip, trying to buck 16 volts to 5 volts, it just shuts down altogether, right? So that's kind of what we're looking at right there. Okay, so the equation here, I think I made this one because we just understand how a voltage divider works and we understand what thresholds we're trying to get to, then that's kind of how I made this equation. So V shutdown equals V off times RENB over RENB plus RENT. So RENB is REN bottom and RENT is REN top. And so what I ended up choosing for RENB was 10K. Again, we just arbitrarily choose this. So this is going to look a lot like whenever we did just the calculations for our feedback, right? You arbitrarily choose one value and then you solve for the other ones. V shutdown is equal to 0.4 volts. We get this value from the data sheet. This is the value at which the V shutdown is active. And so 0.4 volts equals 20 volts is the value that we choose. So V off is 20 volts. We said, so if the power supply, if that external brick for some reason outputs anything less than 20 volts, shut down the power supply altogether, okay? Because we're making it for 24 volts. And so 24 volts is what we're classifying as under voltage. And so we're gonna execute the under voltage lockout sequence. So 0.4 volts equals 20 volts times 10K over 10K plus RENT. RENT is equal to then 490 kilo ohms. And again, I'm saying 0603 package, 1% tolerance, and 1/10 of a watt rating on that puppy. Completes the section for our component selection. Go ahead, drop a comment down below if you have any questions about how I went about choosing these. Like I said, the data sheet I think was pretty straightforward on this one. So, and then the next step, I guess now is going to be, we're going to talk about layout stuff. So I have a bunch of layout notes and I'll show you how I went about doing that. Alrighty, so now we're going to take a really in-depth look at the PCB layout and the PC board design for this project. So yeah, one thing I didn't mention, I guess, in the component selection part is, I guess, our connectors, which are technically components. I mean, they're on the schematic, but they're just typical 2-position Molex connectors that are appropriately rated for voltage and current. So they're nothing really special or anything like that. Basically what I'll cover, I think there's gonna be like 3 main portions to this. So I'll talk about general board optics, or like general board details, like layers and thickness and copper and stuff like that. Then we'll go into component placement, and then we'll talk about the routing and stuff like that. So real quick, let's just switch into 2D layout mode so we can zoom in on this. So yeah, this board is actually not very big at all. Look at, like, I have the dimensions up right here. So we have 3.11 centimeters by 2.63 centimeters. So not a big board at all. I mean, we squeeze everything as small as we possibly could on here. And honestly, we probably could have got a little bit smaller if I was better at layout, but you know, here we are. So let's just take a look at some of my notes I have for the PCB layout. So general board notes. So this is a typical 2-layer board with 1 ounce copper. So usually what I will do, unless I know this board is extremely complicated and complex, I will start out with a 2-layer board, right? And typically they're both signal layers, so they allow me to freely route on both sides of the board for whenever I need to, so I can place vias and do whatever I need to in order to kind of optimize my component placement. Because if you remember, we had a couple notes previously during the component selection phase where it said, got to place these components really close to a certain part of the chip or something like that. And so being able to route on both sides of the board will allow you to do that. Typically, if you go to 4 layers, what a lot of times you'll see is 2 of the layers become power planes and or ground planes. So like one layer will be like a power plane where you might have like 3.3 volts, 5 volts, 12 volts all running on that plane. And then you'll have like a ground plane for things to quickly connect to ground. And that's what you see with a 4-layer board. But with a 2-layer board, usually they're both signal layers, and then we utilize copper pores for our ground connections. And then you'll have a copper pore on, at least what I did was I put a copper pore on both the top and the bottom. And I guess that's a good quick tip to start out with, is that you want your board to be symmetrical, meaning if you look at my top layer, you see this entire area of red right here, and then we go to the bottom layer and you see the blue and the red basically take up the same amount of space. You do want this, and the reason is during the manufacturing process, if your board is too unsymmetrical, you get uneven cooling, and then what will end up happening is the board will warp one way or the other depending on if there's too much copper on one side or not, because it will cool unevenly, and there's like thermal expansion associated with metals and stuff. And so what you always want to do is just throw down a big old fat copper layer, make your board nice and symmetrical. Even though I only have, if you look at this, I only have 2 little traces routed on the bottom, so I could have made this whole thing just red on one side and then the blue on the other. Could have just literally been 2 little traces, but I knew that would have really been a bad idea for manufacturing purposes, so I made sure to put a copper pore on both sides. And it also helps with grounding and EMI and signal integrity for signals on the board, so it kind of has that benefit as well. The 1 ounce copper, that's a very common copper weight. Don't do anything special, like just stick with 1 ounce as much as possible. You can pretty much get everything done you need to with 1 ounce copper. I mean, maybe 2 ounce copper if you're like some extremely special case or something. I don't know, nothing too special about dimensions. Like usually what you'll have is the product spec, like the mechanical engineering department or whoever is making the housing for your board will typically come back and say, we got this much space for you, and so make it this big. And so I just kind of said, I want to see how small I can make it. And that's kind of what I ended up doing. So yeah, the other thing I want to talk about is I put 4 M2 mounting holes on this board, because this is going to be something we're going to start doing on all our boards, is that pretty much every board is mounted into its case. You don't want it rattling around in there. So you're going to screw it down with something. And what you want to end up doing is, and we'll go to 3D view to see this, is you want to make some mounting holes. So we got 4 corners with mounting holes. So what it does is a screw goes through here, and then you have a nice metal plate. This is just a regular old through hole that's just really big. And what it ends up doing, so it's nice, strong, robust structure for the screw to clamp down on and hold the rest of the board in place for us. And so I end up putting 4 of those bad boys spread evenly across. We want to spread it evenly across the board so we can easily clamp it down. So that's pretty much everything I have to talk about. I mean, maybe we can briefly see. I don't think I have anything on our layer stack manager. Like, it's nothing like it. I think I did nothing special, but this could help just for visualization purposes. So here we have top layer, which is signal, 1 ounce copper, or a nice dielectric. Bottom layer is signal. These are all the default settings in Altium. Like I said, you'll know if you need something special for sure. So if you don't think you need something special, just go with default. And so yeah, okay, so the next thing I want to talk about is component placement. So I get a lot of these component placement tips. If you see, I have a whole bunch of them. I get those from the data sheet. It kind of tells you, if we even look at the data sheet. Honestly, if you look at the data sheet, it does a lot of work for you. It has a layout section. So there's, first of all, it gives you this whole wonderful list of notes, some links for learning more about layout. Definitely recommend that. If you scroll down, it also gives you some conceptual understanding of what needs to happen here. And then it gives you like a nice little diagram. So this is something that you'll see with better and better data sheets will have wonderful diagrams just like this. And so this is extremely helpful when it comes to actually doing your layout. So I kind of followed this stuff, like the recommendations here. Let's see what our notes are first. So inductor L1 and switcher IC U101 will heat up a lot. Avoid placing them too close together. Utilize large copper pores to act as heat sinks. So the note I have for that, and so let's just go in and we'll hit view and we'll do 3D so we can see. So this is our L1 right here. So you can kind of see, and it's kind of almost more visual from this section, is that, see this little outline right here is a copper pore. What I did not do was I did not just make a trace. I utilized a, let's see if it, yeah. So right here, this is a copper pore, which connects a 5-volt version of our inductor, and then here's all our capacitors, and it has the 5-volt section of our, has the 5-volt section of our output connector right here. So this is kind of the, instead of just using, because what I could have done is just make a trace that goes here, a trace that connects here, a trace that connects here. Instead of, no, we have a nice large open copper pore because it has lower conductivity. It's so it's more conductive. Or I say lower, it has lower resistance, so it's more conductive. So it's not going to heat up as much with high currents. 2, it's going to act as a nice heat sink because it's a big flat piece of copper. That's kind of how that is. I think I did the same thing as much as possible. So yeah, here's what I end up doing is I make another copper pore right here. And then what I ended up doing was I just made some really fat traces. So I think I had accidentally, so right here. So this is just connected a big old fat trace to this pad. And so we just kind of have a full area of copper that is touching this pad to this pad right here. Instead of what typically happens is you get these little thermal relief marks. Right here is the default connection for a polygon pore. And I didn't really like that. So I just made these nice big old thick traces here just to fill in the spaces, and that's kind of how I did that. So it is for both sides of the inductor because I know both sides are going to heat up, and then we also have, so it's kind of hard to see, and I don't know how much more visible I can make this. So this is our little chip right here. So we'll try to go in 3D view. So this is our chip, and this is actually more visible to see. So we have right here in the corner C1, which I think is our bootstrap capacitor, right? So let's take a look at C1 is our bootstrap capacitor. So it's going from the boot pin to our switch pin. So C1 is connecting from this little pin right here to this large copper pore because it's also connected to the switch node of L1. Like I said, these two are going to be heating up a lot. So make sure you have some nice large copper pores to act as heat sinks right around them. So that's kind of what we did for that. Then we got C1 coming in right there. Like I said, utilize large copper pores to act as heat sinks. Exactly. All SMT components are placed on the same side of the board to reduce manufacturing costs. Ooh, this is a great meta tip, right? So if you look at this, nothing. Let's flip it over on the back. You got nothing back here, okay? And the reason why is because if you understand the manufacturing process, you know the way they mount surface mount components is the board. Basically, long story short, it's cheaper if you mount all the surface mount components on one side. So it's just a lot more convenient. Just do that if you can. Just a meta tip for you right there. So input capacitors C2, C3 are placed as close to the chip as possible per the data sheet. So data sheet says do that. So C2, C3. Let's take a look at C2 and 3. So there's C3, which is like literally as close as you can get it to our chip. It's right there. And then there's C2 right next to it. So let's do view again. So what I did was I utilized, so this has to be on the 24 volt side of things. So the way it ended up working out is that, so this is the VN pin right here. So I just have a nice trace going in, connecting all of our 24 volt connections right here. And one reason why I didn't feel the need to do, like I mentioned over here, large copper pores is because, so if you remember, if you know like the basic physics, or I guess I could say thermodynamics of what's happening, we know that P in is equal to P out divided by your efficiency ratio. So you have significantly less current. So we're having significantly less of input current into our chip. Like I said, you don't need to worry about this trace being extra thick because it's not carrying a lot of current. So that's kind of what I did for that. And then the bypass capacitor C7 is close to pin 7 of U101. All right, so let's take a look at our C7. And then C7, which is our timing capacitor, right? Or the capacitor that goes into our timing circuit. So that's C7. So let's look on our board and we'll see where C7 is. So there's C7 and it's connected to pin 7 of our pin 7 and pin 1, but it says, the notes say close to the pin 7, right? So because this capacitor is connected to 2 pins, but we had to prioritize pin 7 over pin 1. And so that's kind of what we ended up doing. And then what we did was, so here's this connected to pin 7. And then what we did was we ran a via. So here we have one connection. This is going into pin 7. And then we ran a via, which goes to the second layer. And then it comes back up. And then we connect to pin 1 of our chip, right? So because pin 1 and pin 7 have to be shorted, and there wasn't really an easy way to do that because we have to have a really good ground connection that was basically cutting this in half. So we ended up having to use a via. And then so the via I used was, looks like this is a 2010 or a 1020, you should say. So the whole size is 10 mils, diameter is 20 mils. So that's what I used for that. And then like I said, we make sure that pin 7 is shorted to pin 1, and then we have our timing capacitor right here, which is pulled up real close to it. It says place feedback divider as close as possible to the feedback pin is another component placement tip it has for us. So R3 and R4 need to be as close to the feedback pin as possible. So let's take a look. We have R3 and then R4 is right here. So this is R3 right here, and we'll actually go in. Let's go into 3D mode to look at it. So we have R3 right here, R4 right here. Those are as close to the feedback pin as possible. So here's the critical connection right here. So this is where the voltage divider, quote unquote, output is right here at this pin. So we go right in, sneak in here, and then we connect right to pin 8. And then we have this one's grounded, of course, and then this one is connected to the 5-volt copper plane. Right, so this is another reason why utilizing a copper plane on the output was helpful, is because this would have to just go into, like, we just have traces everywhere, right? We'd have 1, 2, 3, 4, 5 traces all trying to figure out where to connect to. And so a copper pour like this made everything a whole lot easier for us. Okay, so yeah, so that pretty much covers everything we need for the component placement. And then the connectors, what I ended up doing was I just kind of shrunk them in as close as possible. I could have pulled this connector in maybe a little bit more, but I didn't really think it mattered that much because it was just, I mean, shrink our board size, which is nice, but it wasn't, necessary for this project, so to speak. Everything else, like I said, I just made these capacitors as close to this other capacitor as possible. Tried to follow, and let's take a look at this data sheet. So that's kind of what I tried to follow right here. Is if you look like the C out and C in, and then C in as well. So I kind of tried to follow this as best as I could, right? And so that's kind of why we ended up, that's kind of how things came out. And so that's kind of another like broad trade. If you follow the data sheet, you really can't go wrong. So I think you'd be just fine if you just follow what the data sheet says. Routing and copper pores. So first note, we use copper pores as much as possible. Wide traces have lower impedance. So instead of just making some big old, really thick, wide copper trace, we use just a copper plane or copper pore instead. And like I said, because that's the whole point of using copper pores, a really wide trace that has low impedance, high conductivity, acts as a heat sink, right? Those are the main reasons you use a big old copper port. A couple of vias were used to keep signal pathways short. So like I said, we could have gotten away with not using any vias. Like maybe I could have taken this signal and routed it like all the way around here or something, but it ended up making the layout much simpler if we just used a via and then just short really close to right here. And then I guess, the same thing. So this is our input under voltage lockout circuit. So again, I just kind of scooted these up as close to our pin as possible, and then did a little connection, and then ended up using a via to get to the 24 volt line. Let's see if we go on 2 as well. So because that needed to go to C3. Basically, it could have gone all the way over here, but this was a shorter pathway, right? And it would have eaten up less copper, right? Because if I routed this through here, it would have eaten up a lot less copper, and I didn't want to cut off this ground connection. So that's kind of what we did for that. I just spotted a way I could have improved this probably. And if you remember my whole mantra of 0603 is good because you can route between it. So what I probably could have done was I could have taken this 24 volt, routed it through here, and I bet I wouldn't have had to use a via, because this would have been nice and short, because you wouldn't have cut off this ground connection by going around like that, and would have kept it nice and short, and so you wouldn't need a via either. So I think if I had followed my advice of routing in between 0603s, it could have made the layout a little bit better. But you live and you learn. Oh, lastly, I guess I'll cover this. So pin 2 in this layout is unconnected or not connected. If you look at pin 2 as the power good signal. So a lot of times, like I said, the power good signal, this pad would be connected all the way back to a processor somewhere typically, right? That's usually what, I say usually, this is all the time. If you use the power good signal, it goes all the way back to a processor. Maybe in some cases you could have some circuit that activates as a result of this flag being pulled low or something, but a couple of videos we use continue about the short, large ground planes on both layers to help with shielding and heat dissipation again. So yeah, let's just copper ground planes. I lay them out, cover majority of the board here. I make sure the net that they're attached to is the ground net, and then so that's kind of why you see, so it's connected to the ground planes right here. What else? I don't have these mounting holes on the ground net because they just don't need to be ground. They don't need to be connected to anything to work, so it's just fine. And then on the bottom layer, we also have our ground net, right? So we'll see this connected to ground as well. So yeah, that's kind of pretty much everything I did for the actual PCB design for this project. Like I said, go ahead and drop a comment down below if you have any questions for me. And if you made it to the end of this video, thank you so much for watching, and hopefully I will see you in the next one.